Welcome back, listeners. So, today we enter the world of passive filters. So, filters are the gatekeepers of signals. So, they decide what gets through and what is thrown away. So, today we'll demystify the four passive filters you will see everywhere. So, they are low pass, high pass, band pass, and band stop. So, by the end of the lecture, you will know what each one does and how its cutoff behaves and where engineers use them. So, let's move forward. So the quick objective of today's class is to understand each filter's frequency response, learn the simple cutoff formula for RC filters, and then see the center frequency idea for the bandpass filters and learn the practical applications. So to start with, first let us see what is low pass and high pass. So these are the filters which will pass low frequencies and attenuate high frequencies are termed as low pass filters. So here on left hand side we see a response which is obtained while operating on a low pass filter. So here the response shows that whenever we are changing the frequency after a particular range of frequencies, the response or the amplitude of the signal is decreasing. So that means it will be sending a particular range of frequencies and attenuating the remaining frequencies. So that is why it is known as low pass filter, because it is passing the low frequencies and attenuating the high frequencies. Then moving on to high pass filter, so it will pass high frequencies and attenuate low frequencies. So you can see in this graph, so it is allowing the higher frequencies to pass and attenuating the lower frequencies. Then moving forward, we have band pass filters. So in band pass filter is actually a combination of low pass and high pass filter. So the sequence is, first we are going to have the high pass filter where it will start from a particular frequency and it will allow the remaining frequencies, and then it will continue with the low pass filter where it will be passing a particular frequencies up to a limit, then it will attenuate the remaining frequencies. So that means we are going to have a signals of this format. So it will be allowing a particular range of frequencies and it will be allowing up to a particular range of frequencies, then it will attenuate, and initially also it will attenuate. So this is called as the band pass filter. So now the last and final one is the band stop filter. In band stop filter, what it does, it passes the frequencies outside a band and attenuate the frequencies within the band. That means it will reject a particular range of frequencies. So to see that, let us go through this. So as you can see here, it is rejecting a particular range of frequencies. It is becoming zero at that frequency, and then again if we increase the frequency further, it is allowing the remaining frequencies. So this is a band stop filter. So now how these filters will operate, what are their frequencies, what are their operating frequencies, or from where it will operate. So let's see one by one. So first let us consider the ideal response. So in ideal response, first let us see the low pass filters. So here as we can observe, in the low pass filter it will allow the low frequencies. So in ideal form, if we consider omega c to be the cutoff frequency, then it will allow up to omega c, and after omega c it is not going to allow any range of frequencies, so which is shown here in this waveform. This is the ideal response of low pass filter. Now moving on to high pass filter. So in high pass filter, it will allow after the cutoff frequency. So if the omega c is the cutoff frequency, then it will allow after the cutoff frequencies. Then coming to band pass filter, it will allow within a range of frequency. So here it is given as omega 1 and omega 2. So within this range, it is going to allow, and remaining signals it is going to attenuate. Then band stop filter is, it will reject a particular band of frequencies. So within omega 1 to omega 2, it is rejecting this band of frequencies and allowing the remaining. So whatever signal is allowed by a filter, or the band of frequencies which is allowed by a filter, is known as pass band, and whatever signal is rejected by the filter is known as stop band. So here after omega c, this is the stop band area and this is the pass band area. In high pass filter, this is the stop band area and this is the pass band. In case of band pass filter, we have this is the pass band area and we have two stop bands. And in case of band stop filters or band reject filters, we have two pass bands and one stop band. So this is the ideal frequency response of the filters. So ideally the filter should behave in this manner, but practically it is not possible. So suppose if we are building a low pass filter at a cutoff of 100 Hz, then it will allow around 110 to 120 Hz. Then it is going to attenuate the remaining. So similarly in case of the remaining filters. Let's start with the filters one by one. So first is low pass filter. So the filters that we are discussing here are passive filters. So they use only components like resistors, capacitors and inductors. Would not have any transistors or any kind of op-amps. Because if we consider transistors and op-amps in our filtering circuit, then it becomes active filter. So that is why, as you can see in the diagram, we are having two components. One is resistance, second one is capacitance. So this circuit will behave or will generate the low pass filter. So if we consider the output across the capacitor, then it will behave as a low pass filter which will attenuate the higher frequency components. The capacitor blocks high frequency signals and allow low frequencies to pass because high frequencies make capacitor impedances small. So the signal gets bypassed to ground. So there is a property of low pass filter. So as we are getting the output across the capacitor, so this property will follow and will receive the signals which are lower in frequencies and the frequencies which are on the higher side or on the high frequency side will get attenuated. So now moving ahead, if we write down the transfer function, so transfer function is given as the ratio of output voltage to the input voltage. So as you can see here, the ratio of output voltage to input voltage is V naught by V in. So V naught is given as I into R. So here the current is I, current flowing through the circuit is I, and then IT, function of time t, and the resistance is given by 1 by j omega c. Now if we write down for the input voltage, so if we write down the KVL equation, so that will be VIT will be equals to current into the impedances. So impedance is given by R plus 1 by j omega c. So now the ratio will be 1 by j omega c divided by R plus 1 by j omega c. Now if I this equation, so we'll be having this format 1 by 1 plus j omega RC. So the cutoff frequency is given by omega c is given by 1 by RC. So if we put this here, then the value of h omega c will be, so this two term will get cancelled and the remaining will be 1. So it will be 1 by root 2. So the value of the transfer function or the gain is 1 by root 2. So that is why, as you can see, the function will be attaining a value of 1 by root 2, which is equals to 0.707. If the maximum is 1, then the cutoff frequency point is given as 0.707. So this represents the low pass filter. Moving on to high pass filter. So in high pass filter, we reverse the capacitor and suddenly the story flips. The high pass filter blocks slow changes and allows fast variations. So as you can see here in this diagram, which contains a RC series circuit and the output is across the resistor. So here DC is completely blocked, only dynamic and high frequency changes pass. So which is perfect for removing offsets, coupling AC signals, and eliminating drifts. So if we see the response, then as you can see here, the lower frequencies are attenuated and higher frequencies pass. So this is the ideal response, and the practical response will be gradually increasing from around omega c, the cutoff frequency value, and later on it will be providing or allowing the remaining frequencies above omega c. So now if we see the transfer function, the transfer function is given by V naught by Vi. So now here the output is across the resistance. So we have resistance on the top. Below we have the total impedance, so which is R plus 1 by j omega c. So after simplifying, we have this relation. So now here the cutoff frequency is same, which is given by 1 by RC. So if you put here 1 by RC, then the output will be, so this term will be providing the output of 1. So finally, the value of the transfer function will be 1 by root 2, which is similar to the low pass filters. So here also the cutoff frequency will give a value of the transfer function or the gain as 0.707 if the maximum is at 1. So this is the high pass filters. Now moving ahead, next is comparing low pass and high pass filters. So as we have already discussed, so the low pass filters pass low frequencies at high frequencies, and the cutoff is omega c equals to 1 by RC. Then in high pass, it passes the higher frequencies and attenuate the lower frequencies, and the cutoff is similar, which is omega c equals to 1 by RC. So the both filters share the same cutoff frequency formula, right, as you can see here, and they their behavior on passband and stopband are totally opposite. The passband for the low pass filter becomes the stopband for the high pass filter. So that is low pass and high pass filters. So now let's go for the band pass filters. In band pass filter, as we have discussed, it will pass a particular band of frequencies, as we can see here in this response, and this is the practical response. So similarly, here also the cutoff frequencies will reach at a value of 0.707 if the maximum is 1, and the circuit for the bandpass filter is given by RLC components connected in series, and the output is measured with respect to the resistance. So this also is a response of the resonating circuits. So as we already know, we have discussed in our earlier classes. So if you want a particular band of frequencies and block remaining, so that is the bandpass filters. So this can also be considered as combination of high pass and low pass. If you see, the first half of the cycle represents the high pass filter and the second half represents the low pass filter. So at resonance, inductive reactance and capacitive reactance cancel each other, as we know, and only signals near that frequency get amplified at the output. That means it behaves as resistive during this point. So this is the idea behind band pass filters. So we can use the RLC circuit as bandpass filters by determining or by considering the output across the resistance. And if we plot the transfer function, so it will be V naught by Vi. So the output is across resistance. So that is why we're having resistance here, and the remaining overall resistance or the impedance is given. So that is R plus j omega L minus 1 by j omega C. So the center frequency here is different from low pass and high pass filter. It is given by 1 by root over LC, as we already know. This is the function that we have obtained in case of resonating frequencies. So this is the center frequency, that means the value of omega naught. Next, the final is band stop filters or band reject filters, which is also known as notch filter. So it is the opposite of band pass filter, and it blocks one slice of frequencies while letting all the other frequencies to flow. So in notch filter, the cutoff frequency at omega naught So it rejects the frequency within this range. So the range is given here as omega 1 to omega 2. So in between these two frequencies, the signal will get attenuated and the remaining signal will get passed. So now if we consider a sharp or a narrow bandstop filter, then it is known as notch filter or narrow band reject filter. So this is H omega, this is omega. So now this frequency, so a famous or a well-known filter that we have to build is a 50 hertz cutoff frequency. That means 50 hertz notch filter we used to build for removing the power line noise. So for doing that, we eliminate the 50 hertz frequency during the operation and the remaining frequencies are passed. So to do that, the bandstop filters help, and particularly the narrow bandstop filters help. So now if we check the transfer function, so transfer function we determine with respect to the capacitor and inductor, that is the output is across the capacitor and the inductor. We determine the output across these two components. So if we are determining across these two components, then across output will be having omega L minus 1 by omega C divided by the total impedance, which is R plus j omega L minus j 1 by omega C. And the center frequency is, as we already know, it is 1 by root over LC, which is nothing but the resonating frequency. So this is the bandstop filter and the response of the bandstop filter. So I hope you have understood up to this. So now let's see what are the key parameters that we have to keep in mind during designing of these filters. So the first thing is the cutoff frequency, and we have observed that the cutoff frequency lies at a amplitude of 1 by root 2 or 0.707. Then the center frequency in case of band pass and band reject is nothing but the geometric mean of the upper and lower cutoff frequencies, right? And the third thing is the transfer function. So the transfer function is the mathematical relationship between the output and input voltages. So this is what we have discussed and we have seen in all the filters. So now moving ahead with the filter applications. So where do we use this filter actually, or in real world, what is the use of these filters? So the practical examples and use cases include where you will see this are like audio crossovers, so low pass filter and high pass filters, and then radio front ends where we have band pass and band reject filter applications. Then in case of power supplies where we have low pass and smoothing, and in case of biomedical signal processing where we require the use of all the filters, that is low pass, high pass, band pass filter and band reject filter, and particularly to remove the power line noises, that is the 50 hertz noise. So these are the various applications of the filters. So let us consider a practical example of filters. So as you can see, this is a schematics of EMG detection. So EMG is the signals of our muscles. So that means the signals that is generated in the muscles can be detected, and the schematics or the detection procedure includes various components in which we also have high pass filter, low pass filter and notch filters. So let's see how is the behavior or what is the output of these. So here on the left hand side we obtained the amplified output, which is a raw EMG signal, and on the right hand side this is a filtered EMG signal. So as you can see, all the unwanted components of the signals are getting removed by the filters. This is the full circuitry as you can see here, which also shows some other applications. So now our the required part which is important to us is this graph. As you can see here, this yellow color graph which shows the filtered output. So this is the response of the signal. Now the other part represents the full wave rectification, which we have discussed in full wave rectifiers. So this is the practical application of full wave rectifiers. Then next, as we have discussed in the filter classes, The application of capacitor filter is shown where the envelope of the signal is getting detected. Time example where we use the filters. So now if you want to go through the simulation of these filters, so you can go through the video which is given in the description and also given in the comments. So you can go through that and see how the filter responses are determined using the schematics. So let us consider a quick exercise. So let us consider a low pass filter with a resistance value of 1 kilo ohm and the capacitor value is 100 nanofarad. So to determine the cutoff frequency as we know is given by 1 by RC. So the putting the values, so we obtain the cutoff frequency to be at 1.59 kilohertz, right? So this low pass filter will pass the audio base and block the higher treble above this range. That means 1.6 kilohertz. So now you know what each passive filter does and how to eliminate cutoffs and where to use them. And in the next video we'll build and simulate this, so you just go through the PSpice simulations, so for passive filter topologies and frequency sweeps and visualizing the minus 3 dB point in PSpice. So don't miss the next video. So I hope this is helpful for you, and if you have any doubt you can put those in the comments. We'll try to solve your doubts. So thank you for joining. Keep learning, and please do share and subscribe so that you don't miss any videos. Thank you.